Thank you. So what I'm going to talk today about is more or less my project during my PhD, which is related to the interactions of internal tides and mesoscale eddies. And during this talk, especially, I want to focus on the evolution of one tidal beam in an eddying ocean flow. And for this, I first want to introduce you to the region I'm looking at. So we are located in the Southeast Atlantic with the African coast on the western side. And right in the middle, we do have the Walvis Ridge, which is a known generation point of strong internal tides, especially here or during the whole talk, I will solely focus on M2 tides. And furthermore, a part of just generating strong tides, we do have these strong parallel tidal beams visible in the mean energy flux. And what I mean with tidal beam here are these okay, don't have a pointer, but you see in red, which is indicating to you the flux, which like beams which start at the Walvis Ridge and then propagate into the to the east into the Cape Basin. And these beams is what I'm really interested in, and especially the one where you can see these green stars on and white dots, which are actually observable observational instruments, which are still in the water and we will recover during the next month. Furthermore, we don't just have our tides, we also have a lot of eddies. And these eddies are generated at the Agulhas retroflexion and take the pathway of this blue shading. So right over the Walvis Ridge and also right over our tidal beams. And having both tides and eddies is right where I want to be and to study how the energy flux, how the energy of such tides is changing. And for this, I'm looking at the energy flux of my internal tides, and we already heard some things about how to calculate energy fluxes today. I do it a bit more simplistic. My flux is just calculating the U prime times P prime over 2 wave periods and integrating it over the whole water column. To get my anomalies of velocities and pressure, I first take out the barotropic component and then filter for my M2 frequency, and then do the flux calculation. And with this, I don't only just get an amplitude, but I also get a direction in my horizontal plane, so an XY direction of the flux. And I know it's a bit hard to see on this image, and I don't have a pointer, so it might be a bit hard. But if you look at this on this plot, on the left-hand side, we would again have the Walvis Ridge. So around 2 degrees east, we have the generation of the internal tides at a slope which has a width of about 1 degree. So a quite wide area where we have this generation of tides, and then have energy fluxes to the southeast. So to the east, sorry, and a bit of southward component, and you see it quite coherent, up to 7 to 8 degrees east, and this is very close to what we also saw in the mean energy flux before in this first picture I showed you. And the only difference is that this one is only average over 1 day, while the other one is average over multiple months. Okay. So one could assume that these mean fields actually represent my tidal beam or the energy fluxes quite well. In the background, you can, however, see that there are these eddies which I talked about. So we do have right here in green shading is the velocity, the amplitude of the velocity. So we have 3 eddies, 2 cyclones and 1 cyclone for this time snapshot with velocities of around 2 meters per second. And if we look now a few days later, we see a very different picture for the energy fluxes. First of all, what is quite easy to see is that now on the Walvis Ridge, the fluxes are much diminished, of an order of 10 to 100, lower than just 6 days before. Furthermore, it's not as coherent anymore, and the strength of the energy flux greatly varies across the tidal beam. And not only the amplitude is changing, but also the direction. we not only have these eastward fluxes, but also some which really go to the north or to the south. And for one, this might be associated with the spring neap cycle, so that especially the amplitude is changing across our throughout our month, but also the orientation of the tidal beam shifts in time. And this is what I would think is, or what I will try to show you is really associated with these mesoscale eddies and how they interact with the tides. You sometimes even see like parts of splitting of a tidal beam, and I will come back to that in a moment. And how I want to show that it's really the mesoscale eddies which impact my tidal fluxes. I am doing, with collaboration of Carsten Eden, ray tracing of modes. So solving this really nice short dispersion relation, which has some parts of what you associate with just the modal decomposition, so the Cn and Kn, but also has an interaction with the mean flow, which are my S terms. So either in a vector form or just in Sx and Sy. So how the background flow interacts with my modal wave. And if you solve this, you can get derived, can trace your rays both in X domain as well as in the wave number domain, and see how both the spatial changes for each time step are, and also the changes in the wave number space, which would in that sense be your refraction. And now I again have my velocity field from the model, so my 3 eddies and multiple different filaments. And I start the ray tracing more or less at the location of the Wolfish Ridge. I don't start directly at the Wolfish Ridge because there the depth is very different and I want to have a more or less uniform depth, but close to where this modal structure really is already quite stable. And yeah, it's running. So this is now for like each time step is around, I think 1 hour apart. And in the beginning, these rays stay very parallel, but seem to converge around, between 6 to 7 degrees east, where we really have a convergence of different ray paths and an overlapping of these ray paths throughout the domain. And it's a bit hard to see. I have it now also in a still picture, but if you focus on the region between 6 to 7 degrees east, then you see that especially in the northern part of these grayish area, it's much more dense, much more refined. A lot more of these initialized rays meet up there compared to the southern part. But it's still quite hard to identify what role each of these mesoscale structures has on individual ray paths, and therefore I want to simplify them. Went on to simplify it even further and look at individual eddies and idealized cases. Further, I want to know that it's even harder to spot, but if you look like really at the end, you see that the dots are actually behind each other. And we don't have any wave-wave interaction in this model, so only linear superposition, but this could maybe lead to a phase shift associated, which would make it even harder to spot in the original way to calculate energy fluxes or via satellite altimetry. Now to these more idealized cases, I went with a similar stratification as we have in the model, and the velocities are also similar, and the size of the eddy is what we see in the normal model. Now we do have a cyclone with a radius of 90 kilometers, similar stratification. I again initialized the mode 1 and M2 waves in the beginning on the left and let it run through, and depending on where these rays meet the eddy, you really have very different refraction happening. If it meets more or less the southern part of the eddy, you have this convergence of ray paths, while if you go into the northern part, you have this divergence of the ray paths. And if this would now be an anticyclone and you don't really change much in the stratification, it would just flip around. So the orientation of our wave vector and the background velocity is really the dominant part in how this refraction is happening. if we now maybe look again to a dipole, so that's also what I have for the specific time in the model. This convergence of ray path is really just amplified. So one can maybe see it just as a superposition of two individual eddies, but if they are connected, you have this amplified convergence or divergence of this ray. And if we now see again, in the southern part, you also have this clustering, and in the northern part, you have this clustering. You could maybe even interpret it as somehow of a splitting of our initialized beam. I'm apparently talking very fast, and I'm already close to my end. So if we go back to the energy fluxes I showed you before, so again, mid of April, where we have this weaker generation, and in general, a quite incoherent tidal beam structure. So not something we would assume if we just look at the mean over months or years. There we see that it's a very complex, that the fluxes have a very complex structure. But I believe that with these idealized ray tracing, we at least can get parts of it, or can explain parts of it already. We started with the rays at the Wolf's Ridge, and they propagate to the east southeast, but they seem to go a bit more to the west or to the south, depending on where they meet their eddies. And yeah, what I'll try to show is that there is some part of convergence happening, or splitting and divergence, really depending on the location of mesoscale structures. What I want you to remember from this talk is that tidal beams are not as stationary in time or space as we might believe if we just look at these mean pictures over which we get from satellite altimetry or mean model calculations. Mesoscale eddies do have a major impact on the pathway of energy. And this might also have really impact the dissipation of energy, because it's likely not homogeneous across the tidal beam, and we don't have this slow thinning out of the energy while it's crossing a basin, but might be much more localized and depending on the background field. And of course, not in every location we do have such strong mesoscale structures, but if we look at this specific region, we really need to take into account the impact of Agulhas rings. So I don't know how much time I spent, but thank you for your attention. And I would just want to leave you with some open questions. And if you have any further question, you also feel to reach out via this email. But the next steps I want to do is maybe look at higher modes and see how they would propagate through such a field. And then maybe also get somewhere in the direction what wave-wave interactions would play a role if we would include them. And then also to quantify the champerability based on eddies and the spring and neap cycle in this model, to see how large the impact is of mesoscale eddies and the spring and neap cycle on the energy fluxes. So thank you.